Okay, so that was the slab geometry. Now we move on to the cylindrical geometry, and we go through pretty much, identical steps, but of course the final results are not going to be the same. Otherwise, we wouldn't do this. So first, why bother about this cylindrical shape? Okay, heat transfer through this cylindrical shell. So here are some examples that I put in. There are many more examples. So here, insulation over a pipe, where the heat transfer could be this way, or here is a insulation over a buried hot water pipe that was just outside our building. So we're talking about heat transfer through this layer of insulation. So you can see it's a cylindrical shell. Other more exotic scenarios could be heat transfer from the inside of uh, the of an animal through its fur. Okay, and likewise here, heat transfer through a layer of fat, for example. So all these are situations that we may be able to simplify as heat transfer through a cylindrical geometry. So now let's keep going. Remember how we get started. We always get started with the most general equation. Now we already dropped out the convection term. Convection term has been dropped out already from this equation. So we have transient and conduction and generation term. But this is the most general governing equation. We have to now write the one that we need for our uh, situation. And so our situation is steady state, and also it is symmetric. So if my temperature here is same as temperature here is same as temperature here, and then if the temperatures are same in this direction, then the gradient in this direction is 0. So the heat, there is not going to be heat flow along this direction. That's why we drop out this term. And likewise, if the temperature here is same as temperature here is along the z direction, then there is not going to be heat flow along the z direction. So we drop the actual term as well. So at the end, then we also drop out heat generation because we're trying to solve for the situation of no heat generation. So then the governing equation comes out to be only this term. And then the boundary conditions, again, it's a second order equation. We're going to need two terms, and it's the inner temperature is given and the outer temperature is given. So those are the two possible boundary conditions. There can be other boundaries. So now we're going to solve the equation. So this is our equation that we want to solve. Instead of expanding the derivatives, I just simply write this quantity must be equal to a constant. And so dt dr is equal to C1 over R, T equal to C1 natural log of R plus C2. So we have two unknowns, C1 and C2. To solve for the two unknowns, we need two equations. So those are my two boundary conditions. So when I use T at R equal to R0 equal to T0 into this, then I get this equation, and then the other boundary condition, T at R equal to Ri equal to Ti. If I use that one, I get this one. So now from these two equations, we have to solve for C1 and C2. how we can do this in a sort of clean way is, suppose I take this one and this one and subtract the second one from t. So then I can write t minus ti is equal to c1 natural log of r minus c1 natural log of ri, which is equal to c1 natural log of r over ri. So from here I can calculate c1 is okay. So let's just leave that part. And so we still have to find c1. So now let's do these two, this one and this one. So I can write t0 minus ti is equal to c1 natural log of r0 over ri, just the same way as this one, like this one. So from here I can get c1 is equal to t0 minus ti over natural log of r0 over ri. Okay, so I have solved for c1, and that is my only unknown here. So I plug that back in, and so now I have an equation for temperature. So let's look at that equation. So that temperature profile is what we just solved, is this one. So here temperature as a function of position r. So temperature as a function of this radius. Now heat flow is again given by simply the Fourier's law. So QR, heat flow at a radius r, is simply minus k times dt dr times the area. Okay, area at that radius. Now the interesting part is this area that we are talking about is the area of a cylindrical shell. So it's a shell that goes all the way, and in that area is not the same whether you when you are at this radius versus this radius. Obviously that area of the cylindrical, the surface area of that cylindrical shell is not the same. Okay, so in general at any r, this this area is 2 pi r l, because this quantity is 2 pi r and times the l. So it's 2 pi r l. So let's keep going. So minus k times this 2 pi r l that we just talked about, and then ddr of this temperature. So we already know the temperature profile, which I plug in here. Okay, so if I plug in, you notice Ti is a constant and all of these are constants. So if you take the derivative, then all you simply get something like this: minus k 2 pi r l times ddr times ti minus t0 over natural log of r0 over ri times ddr of this quantity. So ddr of this quantity is natural log of r minus natural log of ri. So if you take ddr, ri is a constant, so ddr of this will drop out. So I just have ddr of ln r, which is 1 over r. Okay, and now this r and this r cancels, and I get the final expression here. Okay, Ti minus T0 over this. So you notice again the flow is equal to the driving force Ti minus T0 divided by some quantity. So flow is what drives it divided by some quantity. So So the meaning of that quantity is got to be some sort of a thermal resistance. So the thermal resistance for this kind of a cylindrical shell is given by this formula, which is different from what we did for slab.
So, we did slab, and in a slab, if you think of the thickness of the slab, then throughout the thickness of the slab, the areas are the same. Whether I take from here or in the middle, uh, they are the same area. On this side and on this side are exactly same area. This is not the case for a cylindrical shell. So we have a cylindrical shell here, and we're going to see that the areas inside and outside are not the same, obviously. Okay, so if I open up, then this is my inside area, and then this is my outside area, which are obviously not the same. So then the first thing we want to talk about is that this system is different, and here the areas are different from the inside to the outside. But there are exceptions. So instead of this entire thick shell, so suppose I take only a thin layer. So this thin layer, which was a cylinder like that, this is a cylinder, but then for this, the inside and outside areas are pretty much the same. So if I open up, the inside area and the outside area are pretty much the same. So then this one behaves like a slab. So that's exactly we're going to see as a simplification of the resistance for the cylindrical coordinate, that it will become, in the limit, it will become the resistance for a slab.
Okay, now let's see this quantitatively. We already know that the thermal resistance of a cylindrical shell is given by natural log of R0 over Ri divided by 2 pi kL. Now suppose we think of R0 equal to, or R0 minus Ri equal to, sorry about the quality of writing, I'm not using the normal input device. So R0 minus Ri is delta R. So R0 equal to Ri plus delta R. So this is equal to natural log of 1 plus delta R over Ri. So when for a thin cylindrical shell, when the shell is thin, this quantity delta R over Ri is small. So when this is small, when delta R over Ri is small, a Taylor series expansion gives us natural log of 1 plus delta R over Ri, that's the numerator, to be equal to delta R over delta I. So that makes the thermal resistance of a thin shell to be equal to delta R over K times 2 pi R L. Now you see this 2 pi R L is equal to the area, the surface area of this thin shell, which is A. So thermal resistance is delta R over Ka. So how do you think you're going to interpret the thermal resistance of a thin cylinder. I leave this to you to think about. Now we look at an interesting application of the thermal resistance of a cylindrical shell. The question is, as the insulation is doubled, would heat loss be halved in each case for a large animal and for a small animal? So let's look at the problem in a simple way. So we're looking at an identical situation between a large animal and a small animal in every way, um, including the initial thickness of insulation, except in case of the large animal, the interior diameter is much larger than the small animal. That's the only difference, okay? So the question is, as I double the insulation in the case of the large animal versus the small, would the heat loss be halved, or would the resistance be doubled? If the resistance is doubled, heat loss is halved. So remember, the initial thickness is the same. Okay, so for a small animal, then delta R over Ri, or the insulation thickness over the internal radius, that is not likely to stay small for too long. So when this is small, of course we know already that this can be approximated as this one, okay? So when it's approximated as this, then you can see resistance is proportional to delta R. So on this curve that plots resistance versus delta R, if delta R over Ri is small, which is kind of hard to happen for a small animal, because only for very small thickness of fur would delta R over Ri be still small, and that region is given by the linear region of the curve. As you can see, when it's small, resistance is linear. Eventually though, for all other fur thicknesses, the plot is going to look like that, which means it's not linear, which means if you double from double the far, the resistance is not doubling. If we look at the large animal though, it's the same equation, but delta R over Ri, it is possible for it to stay small for fairly large values of delta R. And if it stays small, if the ratio stays small, then of course we can keep approximating it this way, and that just get the linear region kind of for a while. Of course, eventually this curve would also be like that, but it stays linear for a while. And as we said earlier, linear means if you double the thickness of the fur, the insulation will be doubled. So for the large animal, it makes more sense to have a larger thickness of the fur, because the thickness indeed the resistance indeed doubles, whereas for a small animal the resistance does not really double, so it makes less sense. Of course, there will be many other problem from an evolutionary standpoint, that a large amount of power would be very difficult for a small animal to be carrying, and it will not even survive. So we continue our quest for understanding the solution in the radial system by comparing or contrasting with the solution that we already derived for or derived earlier for a slab. And the question we want to ask is, at steady state, is the flux or energy per unit area constant at different radii? Okay, so in both cases, for the slab and cylinder, let's consider two different areas, two different radii in this case over its thickness, and here it's two different locations, 1 and 2. So here the slab has the same thickness as the cylinder. So over these two locations, 1 and 2, energy into the shell at 1 should be equal to energy into the shell at 2. In other words, if you think of this thin shell, whatever is coming in has to go out. Why? Because things are at steady state. The same thing here, whatever is coming into one has to go out, so nothing gets continually added or subtracted from this shell at steady state. So energy in at 1 is equal to flux at 1 times area at 1, and energy in at 2 would be flux at 2 times area at 2. So let's do the slab first. So in the case of slab, the flux is minus k dt dx times area at 1 and the same at 2. Now for slab, the area at 1 and 2, that's area here and area here, are the same. So dt dx would also have to be the same. In other words, temperature profile would be linear. Not so for a cylindrical shell. So for a cylindrical shell, again, flux is minus k dt dr times area at 1 is 2 pi r L at 1. And likewise, at 2, it's flux at 2 times area at 2. Now the area at 1 and 2, area, the inner one and the outer one obviously do not have the same area. So in the outer one has a larger area, and therefore dt dr has to be smaller there so that their product still stays the same. And that's what leads to a temperature profile that looks more like this. So as the area increases, the slope has to decrease. And now you will hear the same idea from a physical example.
Through each layer, at steady state, the same amount of energy flows. So if I take two layers, the innermost layer, let's say, and the outermost layer, so both these layers, through both these layers, the same amount of energy has to flow, which means minus k times the area times dt dr has to be the same for the two layers. Now, the areas are obviously not the same. If the thermal conductivity of the layers do not change, then you have K being the same, and then A times dTdr has to be the same between this and this layer. Since A is smaller here, then dTdr would have to be larger than here, because here A is larger, so dTdr would be smaller. So dTdr would keep changing as we go from inner to the outer radius, which means temperature profile will not be linear. dTdr is not a constant. dTdr would be higher here and lower here. So we'll see that in the profile now. Thank you.